Hello everyone, welcome to another recording of Non-Linearity in the Variance chapter. Basically we were talking about GARCH and ARCH models, and we did learn quite a few very important stuff from those chapters. Now I could have skipped. We ended while we were discussing risk neutrality. Now we can skip diagnostics, but I feel this is very important to understand if ARCH is present or ARCH is properly defined in a model or in your data structure, because sometimes while ARCH produces very important information, is also considered as a problem inside the data. So let's look into these definitions very clearly so that we do not miss out on important definitions. Diagnostics. A summary of diagnostic tests commonly employed to test the adequacy of ARCH or GARCH model will complete this section. These tests, so this would be our 5th video on nonlinearity in variances. So let's move on. These tests, which are designed to ascertain whether or not the estimated model captures the nonlinearity in the conditional variances, are usually implemented using the standardized disturbance. The standardized disturbance is Z, which equals epsilon divided by sigma. Sigma is the conditional standard deviation, and as we know, epsilon is the error in the first part of the model, which is the actual model without the conditional variance portion. So whether or not the estimated model captures the nonlinearity and the conditional variance, where sigma is the conditional standard deviation of the model, the role of sigma in the denominator of Z is to eliminate the ARCH structure embedded in the disturbance term. So when we are taking the fraction of the error term, error of the actual model as a part of sigma, sigma is the conditional standard deviation which captures the ARCH, and when we take the portion, we're left with the part where there is no ARCH. The null and alternative hypothesis from the standardized disturbance is that null is when variance specified correctly, there is no ARCH, and if variance is not specified correctly, there is ARCH. Under null, there is no evidence of ARCH in Z, suggesting the model is specified correctly. If the statistical evidence favors the alternative hypothesis, so this is the first step. We need to run this test and see if the model is specified correctly or not. If the statistical evidence favors the alternative hypothesis, the model needs to be re-estimated with a different specification for the conditional variance, and testing procedure repeated to implement a test of these hypotheses in terms of the standardized disturbance. To implement a test of hypothesis in terms of the standardized disturbance, the error is replaced by estimated error Vt, and conditional variance sigma is replaced by estimated sigma t. 4 types of diagnostics tests are presented. ARCH test on standardized residuals. Apply a test of ARCH-Q to the standardized residuals. Okay. Evidence of ARCH suggests that the initial specification of the conditional variance, conditional standard deviation, this is the conditional variance, is insufficient to be able to capture all of the dynamics in the conditional variance. So we can apply a test for ARCH to the standardized residuals again and see if the variance is correctly specified or not, or we can check for overfitting. Estimate the GARCH model by increasing the lag order for both P and Q, and compute following information criteria. Akaik's information criteria, Schwarz information criteria, Hanna information criteria, where K is the number of parameters in the model, and it is understood that the number of observations t is suitably adjusted for maximum lag order. The best lag order corresponds to where these statistics are minimized. So look for the minimum value within these lag orders, and we try to use that lag order. We know in risk return relationship the lag order represents the risk return. Conditional distribution test. Now this is important. So there's one important thing we came across, which is ARCH is considered to be a problem when the specification, the variance specification, is not properly given or specified. We have ARCH, and so if variance is specified, then we actually do not have ARCH, and that's why it's also important to check for that specification or test for the specification. Then if ARCH is there, then we can check for ARCH on the standardized residuals. We can also check for overfitting with Akai's HANA and Schwarz information criteria. Then we have conditional and unconditional distribution tests. We can use a Kolmogorov-Smirnov test to compare the empirical distribution of Z, which is a standardized residual, with the theoretical conditional distribution used to specify the log likelihood function. So we can simply use the Kolmogorov-Smirnov test and compare the standardized error with the theoretical conditional distribution. Standardized disturbance with the theoretical conditional distribution. Under denial of no specification error, the two distributions should be same. Actually, they should not be different from each other. In case of unconditional distribution test, now conditional distribution is when we are considering sigma. Conditional variance is ARCH and GARCH, we know. Using a Kolmogorov-Smirnov test to compare the empirical distribution of Y. Now let's take the bigger picture, the big population, with the theoretical unconditional distribution of the model. Under denial of no specification error, any difference in two distribution. So basically we are trying to say the distribution of the standardized disturbance and the distribution of Y should not be different from each other. However, we could have drawn the conditional distribution of the model with a log likelihood function. We could have simply taken the distribution of the log likelihood function, and that should have represented the conditional distribution we are talking about here, that you are comparing with the distribution of the standardized disturbance. So you have standardized disturbance estimated, you can simply draw the distribution. You also have the log likelihood function estimated, you can simply draw the distribution, and you can compare with a test if they are same or not. Null is same, alternative is they are not. In case of unconditional, it would be a bit different. As there is no analytical solution exists for an unconditional distribution of an ARCH model, we need to simulate the model for several steps ahead and repeat this many times. For example, 1000 steps ahead we are simulating the model, and we are replicating this simulation for 100,000 times, and we will take the last simulated value from each of the replications. So if you are simulating 100,000 times and taking the final value, you have 100,000 data, and that you are considering as an that data you are pulling together the last data, exactly the last data from each of the replication, and you are thinking considering that as an unconditional distribution of the estimated ARCH model. And also the non-parametric estimate of the distribution. The non-parametric estimate of the distribution can be obtained using a kernel density estimator. So here the step is very simple. Let me repeat one more time. because we cannot simply find a distribution of y when we are doing unconditional theoretical unconditional distribution. We don't have a theoretical unconditional distribution here. We have empirical distribution indeed of the y, but we don't have a theoretical unconditional distribution. We have conditional distribution, but not the unconditional distribution. So how do we draw the unconditional distribution? We simulate under the hypothesis of no specification error. We assume that the simulated model will give us a distribution which is same as y. So with the given specifications or parameters, we simulate the model 1000 steps ahead, and we replicate the simulation 100,000 times. We take the last or the final data of each replication, we pull them together in one column or stock them together in one column, and we take the distribution from that. This is first stage. So we are considering that this column is representing unconditional distribution of the estimated arch. We can also estimate a non-parametric distribution from this vector using a kernel density estimator. So we can have the unconditional distribution, and we can also have the non-parametric distribution, anything we want to use. Then we put them together in the test against the regular y distribution, and it will tell us, it will be the test of unconditional distribution. Quite a few steps, but not bad. So let's move on to section 5, conditional non-normality. An important feature of the volatility models discussed so far is the role of conditional normality. The combination of conditional normality and GARCH variance yields an unconditional distribution. So when we combine conditional normality and the variance that we get from GARCH, we add them together, gives us an unconditional distribution of financial returns that is elliptic. So we get a peaked distribution of financial returns, that is the unconditional distribution. In practice, a simple GARCH model specified with normal disturbance is not able to model. So a simple GARCH model with normal disturbance or standardized disturbance is not able to model all elliptic in the data. So we are talking about a conditional normality and GARCH. But however, a GARCH with normal disturbance cannot capture leptokurtosis in the data. To capture all the leptokurtosis in the data, we need to combine conditional normality with GARCH variance. Consequently, there are three common approaches to generalize the GARCH model to account for leptokurtosis. So when we can develop a generalized GARCH model, okay, so we're talking about generalizing a GARCH model. So this is generalized GARCH model, and this is important, a new thing to begin with. And what is the benefit of a generalized GARCH model? It captures all the leptokurtosis in the data, or should I say the bubbles in the data. The parametric solution to leptokurtosis is to replace the conditional normality specified by a parametric distribution. So the conditional normality in a parametric distribution represents kurtosis, and we want to find the leptokurtosis. So we want to replace the conditional normality by a parametric distribution that also exhibits kurtosis. So no, my mistake, conditional normality does not exhibit kurtosis. The parametric distribution that will replace conditional normality represents kurtosis, and that is the first step towards the solution. We need a parametric distribution representing kurtosis, and we need that to replace your conditional normality so that we have a solution, leptokurtosis solution. Consider a GARCH 1-1 model. Very simple. y equals epsilon, we know, and epsilon is equal to sigma and the normalized disturbance z, sigma z, and we have GARCH 1, right, where this is the ARCH effect, when this is the GARCH effect, where the conditional distribution of z is chosen as the standardized. So the conditional distribution of these normalized disturbances is also representing the standardized students t distribution with 0 mean, 1 standard deviation, and v with v, or should I say this is epsilon degrees of freedom, with the property of the distribution expected value of the normal disturbance being 0, and whether the mean is 0 and variance is 1, and this is the degrees of freedom. And we are talking about the distribution. The conditional distribution is actually students t distribution. The t distribution is the conditional distribution. The t distribution is the conditional distribution. The t distribution of the normalized disturbance is conditional distribution. To find this distribution, consider the t distribution. This is the t distribution formula. We don't need to put in the t distribution formula. All the statistical package already have it inbuilt, where expected value of ET, mean is 0, and variance is simply epsilon divided by epsilon minus 2. You're familiar with that. Defining the standardized random variable, the standardized random variable is that t is e divided by root over, obviously standardized random variable is e divided by root over mean divided by variance, that's all. E divided by variance. It follows that the transformation of variable technique from transformation of variable technique, yeah, we know that. So from if fe we're getting fz, the standardized random variable, we're getting fz from fe, just simply taking a derivative, okay, and we know the value of, well, the derivation with respect of with zt makes this part 1, okay, whatever v divided by v minus 2. ddz is simply taking an absolute zt, okay, let me see, whatever vv minus 2, dz should give you 1, right? And function of et is the whole thing here. So when we multiply the whole thing with the derivative, after all the calculations, we are left with this part, over v by v minus 2. Okay, fine. Which is the standardized students t distribution, which is what is changing here. A lot of things are changing. Okay, the parameter epsilon in this equation provides the additional flexibility required to model the non-normality in the data. Using equations, the log likelihood function is simply summation y by t log theta. So where log of function of z, and this part needs to be memorized, tau b plus 1 by 2 root over pi b minus 2 tau b by 2. So just simply memorize the log likelihood function that is being derived from the t distribution, and this distribution will represent the conditional variance, conditional normality. Okay, this will represent, but theta is equal to alpha naught, alpha 1, beta 1 and omega, right? So we have alpha naught, we have alpha 1, theta is equal to, oh yeah, alpha naught, alpha 1, beta 1, all this coming from the GARCH parameter. And finally we have epsilon. Okay, because yeah, epsilon is included in the log likelihood function, and for that to happen we might need to, because omega divided by epsilon minus 2, so we need to enforce epsilon is greater than 2. So what we are talking about, again we are talking about generalized GARCH, and now the log likelihood function for the generalized GARCH changed with respect to the conditional normality specification being represented with a student's t-distribution, because now the conditional distribution is represented as student's t-distribution, and we are replacing the normality with kurtosis because we want to capture leptokurtosis, and this is the distribution that will capture leptokurtosis for generalized GARCH. So we are using t-distribution, and this is the equation of the t-distribution. We are simply taking the change of variable, using the change of variable technique from t-distribution to the random to any random variable. This is what we have, and so we just replace some values, fe, replacing some values, we get this, right? So set fe this part remains same, is just epsilon minus 2. That's all. See, this part at the upper part remains same. This is epsilon minus 2. Here comes the change. In place of e square we have epsilon z, epsilon minus 2, v plus, everything else remains same. So this changes, so this small part changes. Basically e square divided by epsilon becomes z square divided by epsilon minus 2. In place of epsilon we have epsilon minus 2, and that's how e is transformed to z, and we check that into the log likelihood function. We take a log of this, that's all, this equation, and it becomes pretty simple. First this portion, then plus this portion. We have the log likelihood function, half log sigma square plus half log function of z, and that will capture the leptokurtosis, and the unknown variables are coming from the GARCH equation, alpha naught, alpha 1, beta 1, and from the log likelihood function, the epsilon. When we maximize or optimize this equation, we need to set a condition of epsilon being greater than 2. Otherwise, if it is less than 2 to some extent, then we will get negative values, and the algorithm will not work. Common sense. To derive the covariance matrix of the maximum likelihood estimator corresponding to 20.46, consider focusing on. So now we want to find the covariance matrix of the maximum likelihood estimator. Let's focus on GARCH parameters by conditioning on the degrees of freedom parameter. So we need to put a condition on the degrees of freedom epsilon and focus on the GARCH parameter. So now theta becomes alpha naught. So we restrict. We do not estimate all the parameters. We do not estimate the epsilon parameter, the first derivative, without estimating the epsilon parameter in the restricted model. The first derivative of the observation is gradient, which is this, where the gradient represents 1 plus beta 1 sigma square minus 1 alpha naught sigma square minus 1 alpha 1. Well, this is added with square minus 1 1 plus beta 1 sigma square minus 1. So the second elements remain same, epsilon square minus 1 and sigma square minus 1, these changes in the gradient portion. And covariance matrix is based on inner J, which is the inner product of the gradients, which is consistently estimated by, well, we know that g theta, so we don't need to know this, we just need to know gradient and the inverse of gradient to find the inner product, sorry, the outer product, not the inner product, the outer product, where sigma square in are evaluated as theta is equal to estimated theta. Sigma square in 20.43 and derivative of sigma square, the sigma square and the first derivative are evaluated at theta. The estimated covariance matrix is, well, this is a regular way of estimating a covariance matrix. We know, taking the inverse of information matrix of the outer product gradient, outer part of the gradient. So this is the outer part of the gradient. Inversing gives you the information matrix that also captures the covariance matrix. So what did we learn? We learned how to generalize GARCH by embedding the student's t-distribution into the student's t-distribution into the equation. So first what we had normal disturbance. We did the change of variable technique of student's t-distribution. So basically we changed student's t-distribution completely and embed Z, the standardized random variable or the conditional disturbance, into t-distribution. Okay, so we had a revision when we did that. Very good. You can just push in any variable inside any distribution. So this is how we pushed in with a change of variable technique, and with that we had a new log likelihood function representing our distribution, and that log likelihood function simply captures the elliptic-kurtosis because the process itself is the replacement of conditional normality by parametric distribution. So the conditional normality this is the conditional normality distribution. The D distribution is being replaced by a parametric distribution exhibiting kurtosis, that is Z. So E is become replaced with Z, and then we find gradient and conditional variance of that gradients and the conditional variance of that particular distribution. Very simple. And semi-parametric, a semi-parametric approach, so that is the generalized GARCH approach. In the GARCH parameter, by consider focusing on the GARCH parameters by conditioning on the degrees of freedom. So GARCH parameter is beta 1, alpha naught, alpha 1, beta 1, and our non-GARCH parameters are including epsilon. So you have the GARCH parameters of the replaced distribution. Semi-parametric. A semi-parametric approach to dealing with elliptic-kurtosis is to specify the conditional mean and conditional variance equations parametrically, but to use a non-parametric density estimator just as a kernel estimator. So parametrically we need to estimate conditional mean and variance, but we need to estimate a non-parametric density estimator to estimate conditional mean and variance. Consider extending the GARCH 1 model to allow for a regressor in the mean. So GARCH 1 model, here is the extension. Okay, this is pretty good, right? because this is how we extended our risk-return model. This is how we can include any exogenous variable into our GARCH parameter, where the function of z is to be estimated using a non-parametric method. So what is function of z? It's a parametric estimation. What is function of z? Let's have a look one more time. It's good to revise many times. Function of z is a parametric distribution that exhibits R kurtosis. Function of z to be estimated using a non-parametric method. Now we are going to estimate function of z with a non-parametric method, a kernel density estimator. Estimation procedures are as followed. Choose starting values. Okay. For each t, construct a conditional mean with the extension, a residual, okay, fine, and a conditional variance. Conditional variance is the GARCH. So mean and residual is just now encompassing the extension. So first you initiate, then you construct t. For each t, construct the standardized residual test. So standardized residual is constructed with each t. Use a kernel estimator to obtain a non-parametric estimate of the density of standardized residuals. So as soon as you get z, using a kernel estimator, you obtain non-parametric estimate of the density of these residuals. Non-parametric estimate of the density of these residuals, standardized residuals. So non-parametric estimate of the density of the standardized residuals. FNP may be a kernel density estimator. Evaluate at each observation and compute FNP-ZT. Good. Evaluate and compute. For each t, compute the log likelihood function and maximize the function for the entire sample using an iterative algorithm. Quite a lot of steps for semi-parametric approach. First, initialize, revise the model, find a standardized residual, okay, then estimate, make a non-parametric estimator of kernel density with the standardized residuals, then do the log likelihood function. So yeah, talked about parametric approach of a generalized GARCH model, parametric estimation method of a generalized GARCH model, semi-parametric estimation method of a generalized GARCH model. All of these captures leptokurtosis. A simple approach to dealing with the problem of leptokurtosis is to recognize that the assumption of normally distributed disturbances is resulting in the misspecification of the log likelihood function. So a simple approach is when I am assuming that the normally distributed disturbance Z is the result of a misspecification. Z exists because there is a misspecification in the log likelihood function. Despite the shape of this distribution being incorrect, the mean and the variance of this disturbance are however correctly specified. So the shape is not correct, the mean and the variance are correctly specified. So from chapter 9, which was maximum likelihood estimation in terms of quasi-maximum likelihood chapter. Maximum likelihood estimation in terms of misspecified log likelihood function yields quasi-maximum likelihood estimators of theta. Great. So if the log likelihood function is misspecified because it has a z in it, which is a normally distributed disturbance that causes the misspecification. Log likelihood function misspecified, maximum likelihood estimation from misspecified log likelihood function because it has normally distributed disturbances. Disturbances must be leptocotic, not normally distributed. That's the idea. So we have, when we do the maximum likelihood on the normally distributed me-specified log likelihood function, we have quasi-maximum likelihood estimators of theta that are consistent. The standard errors of theta, known as the Bolers-Woolrich standard errors in the context, are given by the square root of the diagonal elements, okay, always, where Hessian and outer product gradient is this. So very important in terms of concept. Why are we including Z or replacing Z? Replacing our distribution with Z, because Z represents normal distribution, standardized normal distribution of disturbances. So Z is representing standardized normal distribution of disturbances, making our actual data represent normal distribution, where they should represent leptokurtosis, because they misspecified the models, the data are misspecified. Hence we are understanding that there are normal distributed disturbances. Basically, normal distributed disturbances are that portion of the conditional variance that do not have arch. From the fraction, we know how normal distributed disturbances are created. They are a fraction of epsilon divided by the conditional variance, conditional standard deviation, right? So because we have a me-specified log likelihood function, when we have a conditional normally distributed disturbance like Z, the maximum likelihood estimators are known as the quasi-maximum likelihood estimator. That's all. So very important to remember, very important to remember when we are talking about variances. They cannot be normally distributed. They must have leptokurtosis. They are normally distributed because they have standardized normal disturbances. So we can still deal with this distribution when, no matter if they have standardized normal distributed disturbance or a me-specified log likelihood function. A me-specified log likelihood function is quasi-maximum likelihood function. So in a quasi-maximum likelihood function, the distribution is normally distributed. The disturbances are normally distributed. So gradient Hessian, we have studied that. In the case of the true distribution, the standardized student's t-distribution. So when a normal distribution is a t-distribution, an analytical expression of the quasi-maximum likelihood estimator of the covariance matrix is also available. As a me-specified model is normal, the log likelihood function at t is half log twice y half log sigma square half y square by sigma square. So there is a student's t-distribution. So if the distribution is student's t-distribution, so if you have a quasi-maximum likelihood estimator, so quasi-maximum likelihood estimator of theta, and you have quasi-maximum likelihood estimator which has a distribution equivalent to a t-distribution. We learned how we can compare equation if a distribution if that is equivalent to a t-distribution with a testing. We have an expression for quasi-maximum likelihood estimator covariance matrix, which is this, a little change. your distribution equals to t distribution or not. If they are equal, then maximum likelihood function changes. If they're not equal, then maximum likelihood function remains as it is. For the model where conditioning is again on the degrees of freedom parameter, so okay, fine. The first derivatives, gradients and Hessians are these, right? To derive the quasi-maximum likelihood estimator covariance matrix of theta. So now how we can find the quasi-maximum likelihood estimator covariance matrix theta? Expectations. So what is the difference between a maximum likelihood estimator and a quasi-maximum likelihood estimator? Maximum likelihood estimator, a maximum likelihood distribution function is, in case it's misspecified, that becomes quasi-maximum likelihood estimator function, because we should not have a normal distribution, conditional normal distribution in maximum for the t distribution or the maximum likelihood distribution function distribution. When we have normal distributed disturbances, so normal distributed disturbances cannot be there in a actual correct maximum likelihood function in its distribution. It will have effect if there is maximum normality. I mean, if the disturbance term is normally distributed, not leptocotic, then we can call the maximum likelihood function as quasi-maximum likelihood function, and then we have to follow these formulas. This is the log likelihood function, gradient and Hessians. And second derivative, because by definition using the law of attrition, it immediately follows that mean zero, it is a consistent estimate of the true population. Because mean is zero, very important thing from quasi-maximum likelihood chapter we learned that because law of iterated expectation from the first derivation, we learned that quasi-maximum likelihood estimator is a consistent estimator of true population parameter. Quasi-maximum likelihood estimator is a consistent estimator of the true population parameter theta naught. But the second derivative is 1. So the first two terms are 0. Finally, for the outer part of gradient matrix, because it uses the properties of standard distribution, true modular respectively Hessian and gradient, once the three matrices are obtained, blah blah blah. In practice, analytic expression Hessian and outer part gradient for modular of GARCH model with other type of non-normal conditions. We'll see how this is done in practice, but we know how to find gradient, Hessian and outer part gradient for a quasi-maximum likelihood estimator. And in a quasi-maximum likelihood estimator, the disturbance is normally distributed. A quasi-maximum likelihood estimator, the conditional normality disturbance, the disturbance term is not leptocotic. In a quasi-maximum likelihood estimator is a true estimator of the true population parameter theta, consistent estimator of a true population parameter theta naught. Then when we come back, we will do the examples, and this was quite interesting and important. Thank you.